Physics. Physics, all we're going to do today is go over a couple of homework questions. We're going to make today an easy day, Wednesday, hump day. We're going to make it a nice, easy day. And all I'm going to do so far in terms of questions for homework, I got number 11 and number 13. And when I look at them, I know why those were questions. So I'm going to go over those. And that's all I'm going to do today. That's it. And then on Thursday, I will start into section 12.2. A lot of that is theory. There's only one section. So that means this test has a lot of theory on it. This will be I would say 70% to 80% theory test, and like a 30 to 20% math test, because that's just the way this one falls out. Again, it won't be long because we only have one section left to go and it's short. So if I start into that tomorrow, Friday's a day off, yay. Maybe Monday, Tuesday, maybe like Thursday of next week, maybe. I haven't planned yet. I will give you lots of notice. So I'm guessing Thursday-ish of next week. And yes, I know that feels really fast. That's because it is really fast. The good news is there's only one chapter after this, which is also not all that long. And we're actually done. And we're even done all the work I had planned, even if this whole COVID thing hadn't happened. And for the rest of your time, what I'm going to do is I'm going to have an assignment that will cover all of grade 12 physics, not the grade 11 portion, but just the grade 12 portion. I'm going to give you an assignment and you'll just work on that, and it'll be due by June 5th. And that's all we have left to do. So if you're going, what does the next few weeks look like? That's what the next few weeks looks like for you. All right? So 11 and 13 were the two questions that so far, and again, not everybody's finished at this point in the day because I'm recording this at about 5 o'clock. I kind of wait until later in the day so that at least some of you have a chance to do it, so that I can at least get an idea of where the questions are going to be. That's why I appreciate those of you who do it earlier in the day. It does help. So 11 and 13. So number 11 says, some weather satellites orbit Earth every 90 minutes. So their period is 90 minutes. I'm going with purple because my black marker is given out and the purple seems to show up well, and hey, it's my favorite color. How far above the Earth's surface is their orbit? And it has a little hint. Remember that the center of the orbit is the center of the Earth. So here, let me draw you a little picture. So here is, let me do it over here so that I have space. Here is Earth, okay? And here is the little satellite. They want to know how far above Earth's surface is it. But when we figure out R using our formula, when we figure out R is actually from the center of the Earth all the way out to it. And I really just want to know that piece right there. So that's where a lot of people in this end up going wrong. All right. So the first thing I did with this was I changed my 90 minutes into seconds. And there are 60 seconds in a minute, and so it turns out to be 5,400 seconds. So I did that, and we are using the formula r cubed over t squared is equal to g. G times mass over 4 pi squared. All right, I need to clarify something. I'm so glad you guys asked these questions because it gives me a chance to clarify things maybe I wasn't really clear about in the first video. Yesterday I'm going to say yesterday. I don't even know at this point. Yesterday when we did it, we put mass of the sun here. The reason why it was mass of the sun was because we were talking about a planet orbiting the sun. This mass is the mass of whatever the object is orbiting around. So in our case, the satellite is orbiting around Earth. So this is actually going to be the mass of the Earth. And in my head, I'm hearing people go, oh, right now. If you're not doing that, just let me live in my world, okay? So I would do, I'm trying to find R. So I would do R cubed over 5,400 squared is equal to 6.67 times 10 to the negative 11. Mass of the Earth, 5.98 times 10 to the 24th kilograms. Let me just double check that. I'm doing that out of my head. Yep, I'm right. Over 4 pi squared. So again, I would do this multiplied by this, multiplied by 5,400 squared, divided by 4 pi squared. Now remember, it is only the pi that is squared, not the 4. And then I would take the cube root of it all. And what I got was I got 6.65 times 10 to the 6. And some of you might have said, yeah, that's what I got too, but that's wrong. Right. Because remember, they said how far above the Earth's surface is the satellite. When you find R, you find from the center of the Earth all the way to here. So what I need to take off is I need to take off whatever the radius of the Earth is. And that value is actually on the table of planetary data that I gave you on Earth. It says the radius is 6.38 times 10 to the 6. So I'm going to subtract 6.38 times 10 to the 6. And that's going to give me 2.74 times 10 to the 5th meters. Wait, can you hear the squeaking? Just a second. Oh, she stopped. I have a dog that when it's supper, there it is. When it's supper time, she grabs a squeaky toy, any squeaky toy that's handy, and just starts squeaking it. We call it, she's making music. So if you can hear that, that's what that is. All right, so it's 2.74 times 10 to the 5th meters. And just for fun, I converted that. That's like 274 kilometers. So the satellite's actually about, and you don't have to do this. I just did this to kind of, because I can't picture what 2.74 times 10 to the 5th meters is. So I just changed that into something that's a little bit more familiar to us. So 274 kilometers. That's less than the distance between like here and Fredericton. That's how far off the surface of the Earth the satellite is. So while it feels like it's just really super far away, it's actually not that far. All right. That was number 11. The other one that I had a lot of questions on was 13. So let's look at 13 and see what happened there. Says, on each of the Apollo lunar missions, and if you don't know what those were, back in the 60s when they were doing a lot of space exploration, they were sending up lots of different rockets. They weren't shuttles at that point, they were rockets. Apollo was, they named them like Apollo 1, Apollo 2. The most famous one being Apollo 13, which is famous because it didn't make it to the moon. It's one of the worst accidents, space accidents ever, but yet one of the best because the people actually survived. There's a movie about it. I encourage you to go watch it if you haven't seen it. It actually has a lot of the stuff that we're talking about. It actually has a lot of that in there, where it talks about trajectories and gravitational force and those types of things. So it actually, and that sounds boring, but they don't do it in a boring way. It's actually a really good movie. The other movie that would reference some of the things we're talking about, that's a little bit more current, a little bit newer. Again, it's not super recent, but it's more recent than Apollo 13, would be a movie called Gravity. It has Sandra Bullock and briefly George Clooney in it. But it centers around an accident, again, in space. But it talks about orbiting satellites and things, which is where we are going. That question just dealt with it. We're going to deal with it even more in section 12.2. So again, just references some things. So if you're bored and you want to look up something on Netflix, try those two movies. They're good movies. Like, don't let the fact that there's some physics in it turn you off. They're actually good movies. They're interesting. 13, on each of the Apollo lunar missions, the command module was placed in a very low, approximately circular orbit above the moon. So here would be the moon, and the lunar module would actually be in a really low orbit, meaning closer to the surface, orbit around, and then they would send down in these little lunar things, lunar vehicles. They would actually send people down to the surface of the moon. So it says, assume that the average height was 60 kilometers above the surface. So the average height was 60 kilometers, but that is above the surface. So again, from the surface out. When we deal with R, we deal with from the center out. And that the moon's radius is 7,738 kilometers. So the moon's radius is 7,738 kilometers. So when I do my R, when I'm figuring out what my R is going to be from the center of the moon all the way out. So I would actually have to add these two together, which would give me 7,798 kilometers, but I need that in meters, so I'm going to multiply it by 1,000. So that's going to give me 7,798,123. And again, you can put that in scientific notation. I got 7.798 times 10 to the 6th. So if you like it better in scientific notation, there it is. If you like it better not in scientific notation, there it is. Doesn't matter to me. What was the command module's orbital period? In other words, how long did it take that command module to go all the way around the moon once? So, R cubed over T squared is equal to G times M over 4 pi squared. Now again, the M, the mass that we're talking about, is the mass of whatever object it's rotating around. So it's going around the moon, so we would need the mass of the moon. That's not actually on your table of planetary data. It is back in an appendix somewhere, or back in one of the example questions we did somewhere. You can find it in either place. I happen to have it right in front of me because I have the example all done. 7.36 times 10 to the 22nd. Mass of the moon, 7.36 times 10 to the 22nd kilograms. All right, so this time I'm looking for the period. So R cubed would be 7.79798. Oh my goodness, can't write. Times 10 to the 6th cubed over, I'm looking for T this time, is equal to 6.67 times 10 to the negative 11th times the mass of the moon, which is 7.36 times 10 to the 22nd, all over 4 pi squared. So a little bit more rearranging this time because your unknown is in the denominator. I'm assuming though that you can probably do that. My guess is that you didn't get your R right if you had problems with this one. My guess would be that would probably be your biggest problem. But I would cross multiply and then divide and do all that stuff. And don't forget to take this square root. If you're still having problems with that, you can let me know. But my assumption is more that your problem will be in the theory part of it, like you're thinking through the logic part of it versus the rearranging the math portion. If it is the rearranging the math portion, don't feel bad, just tell me that, because I don't know. And so my period I got was 6.1752 times 10 to the 4th seconds. And so I actually didn't like it in seconds, again, just for fun. I changed it into hours just to give us an idea of what that would look like. So there are 60 minutes in a second, so I divided by 60, and then there are 60 minutes in an hour, so I divided by 60 again. And I ended up with that it's 17.2 hours. So in 17 hours, they go all the way around the moon once. Now, the second part of the question was, how fast was the command module moving when it was doing that? All right, so how fast was it moving? That was a little bit more complicated. So let me put the period over here because I'm sure I'm going to want it in seconds. 6.1752 times 10 to the 4th seconds. So here is what I did to figure out. Did I ask you? Wait, let me just double check. Did I ask you to do? I did it in my book, but did I ask you guys to do 13B? I don't remember. So just let me look. 13. No, I did. All right, so B. So B, here's what I said. I don't have a formula with V in it for something going in a circle other than centripetal force is mass times velocity squared over r, right? That's the only formula I know that has V in it for something moving in a circle. And centripetal force, in this case, why is there centripetal force? What force provides that centripetal force? And that is force of gravity. Well, the formula for force of gravity is G is G times M1 times M2 all over R squared. So really, my force of gravity, which is this, is equal to this. So I can shorten that to be G M1 M2 over R squared is equal to M over V squared over R. So let's talk about what these M1, M2 things are. So M1, M2, one of the masses is the mass of the rocket. We'll put R for rocket. And the other one is the mass of the moon, right? Because it's what is rotating and what is it rotating around, the two objects. The mass over here for centripetal force, well, what is the thing that's moving in a circle? It is the mass of the rocket. Okay, so I have this wonderful formula. Now, because I have a mass of the rocket on this side and I have a mass of the rocket on this side, I can just divide both sides by mass of the rocket and I can get rid of those because I don't even know what the mass of the rocket is. So luckily, it cancels out. So I have G, which is 6.67 times 10 to the negative 11th. times the mass of the moon, which I know is 7.36 times 10 to the 22nd over r squared is equal to v squared over r. Okay? And so what I did with that was if I cross multiply here, I have 6.67 times 10 to the negative 11th times 7.36 times 10 to the 22nd times r is equal to v squared times r squared, right? So I just cross multiplied. So I multiplied this with this and this with this. Now I want the v squared by itself, so I'm going to divide this side by r squared. So I'm going to divide this side by r squared. But when I do that, I get v squared, and this r actually cancels the little 2 there. And so now the only place I have r is down on the bottom. And I know what my r is because it's here, right? And so that is 7.798 times 10 to the 6th. Now, that's velocity squared. If I want velocity, I'm going to have to take the square root. So I'm going to have to take the square root of that. So when I did that, I got that my velocity was 793 meters per second. I did not change that into kilometers per hour. I figure I must have been bored by that point and didn't want to figure it out anymore. But you certainly could figure it out if you were curious. I'm curious as to where Harriet is, a sec. But you certainly could figure it out because, let me see, seconds, there are 36, so it would be 793 times 3600 divided by 1,000. So they were actually going 2,854 kilometers per hour. That's what I get. That's really, 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 really fast, which makes sense. It's a rocket. All right, that's all we're doing today. I just wanted to go over those questions. We'll start into section 12.2 tomorrow, which again has a lot of history in it, has a lot of theory in it. For some of you that's yay, for some of you that's not so yay. And again, the test will likely be towards the end of next week, and it will be a more theory, less math. And again, depending on your strengths and weaknesses, that could be a good thing, could be a bad thing. So I will talk to you again tomorrow.